Welcome to week 6. I think we're on week 6, and we're just steadily moving forward. We're kind of having to go through a little bit of a brief course on modular forms here, just because the theorem that I'm going to state to go forward are going to rely on a lot of definitions and terminology and constructions that you're just not going to be familiar with if I don't go through this stuff. So if this isn't necessarily your jam, I understand it, but for those of you who find modular forms interesting, maybe it is your jam. So hopefully I'm appealing to somebody here. Let's remind ourselves what a modular form for SL2Z is. It's a meromorphic function on the upper half plane, such that f of gamma z, where gamma is a 2x2 matrix in SL2Z, is cz plus d to the k times f of z for some integer k, where C and D are the entries in the bottom row of the matrix, and this has to hold for every lowercase gamma in SL2Z. If this function is in addition not only meromorphic on the upper half plane, but at infinity, then we call this a modular function of weight k for gamma, SL2Z. If it's holomorphic on H and at infinity, in addition to all that, then we would call this a modular form of weight k. And if in addition to even all of that, it vanishes at infinity, then we call f a cusp form of weight k for SL2Z. And so today, I'm not going to review everything we covered last time, but today what we're going to do is we're going to have to not only define modular forms for the entire big group SL2Z, we're going to have to learn how to define modular forms for special important subgroups of SL2Z. And you have to be a little bit careful doing this. And I'll just jump right into this. So again, we're going to let lowercase gamma be a, b, c, d in SL2Z. And we're going to let f be a function on H union infinity, where H is the upper half plane with values in the Riemann sphere. And we're going to let k be an integer. And first of all, what we'd like to do is this notation up here in the modularity condition, or sometimes it's called the automorphy condition for modular forms. We want to simplify and compactify this notation down. This whole f of gamma z equals cz plus d to the k f of z, we want to compactify that notation down. So what you do is you take this cz plus d to the k and you move it over to the other side. And that gives you f of z equals cz plus d to the negative k times f of gamma z. We're going to call that cz plus d to the negative k times f of gamma z. We're going to name that something from here on out. We're going to call that f bracket gamma sub k, or f bar bracket of gamma sub k. I don't actually know how to really say that out loud, but I'm going to call it f bracket gamma. And what is it? It's what I just said. It's a function whose value at z is the right-hand side of that automorphy condition. So cz plus d to the negative k times f of gamma z. So the automorphy condition on meromorphic functions on the upper half plane from the previous section, when we were looking at modular forms for all of SL2Z, instead of writing it as f of gamma z equals cz plus d to the k f of z, we could nicely and succinctly write that condition as f bracket gamma equals f for all gamma in SL2Z. Okay, and that's just to kind of keep things simple, do less writing, do less talking, do less notating. And so not only are we going to want to simplify that notation down, but we're going to want to talk about matrices that don't necessarily live in SL2Z. They live outside SL2Z. Specifically, we want to even discuss matrices that live in GL2 plus Q, so the subgroup of the general linear group with positive determinant and rational coefficients. And so you can define f bracket gamma more generally to not just be cz plus d to the negative k f gamma of z, but the determinant of gamma to the k over 2 power times this cz plus d to the negative k f of gamma z. And of course, if gamma happens to be an SL2Z, this determinant is 1, right? So you lose this little piece of the term here, and you end up just with what we started with. But in general, we want this to apply to matrices outside of SL2Z, and here's the correct notion for that. Okay, so the next thing I'm going to do is I'm going to introduce a function called the theta function. This is a little bit of deception though, because I secretly introduced it earlier. You need to introduce it when you're proving the analytic continuation of the Riemann zeta function, but I didn't actually prove that, I just stated it. It comes up in the proof there. Here's what the theta function is. So for the real part of t bigger than 0, so t is a complex variable, we're going to define theta of t to be the sum of e to the negative pi tn squared, and the sum is over all of the integers. Okay. As an exercise, I'm not actually remembering off the top of my head how easy this is to do, but we seem to be interested in the study of elliptic curves and congruent numbers and modular forms and whether or not special functions have functional equations. You can check that the theta function has a functional equation. Theta of t is just 1 over radical t times theta of 1 over t. So you can check this. And we don't care so much about this little theta function here. What we're going to end up caring about big time in the future is this big function that I call big theta. So you're going to define big theta of z to be little theta of negative 2iz. And why this negative 2iz? Well, if you plug that in here for t, you end up with a really nice succinct expression, the sum over the integers of q to the n squared, where q is our usual variable from last time, e to the 2 pi I z. Okay. And so what I'll tell you, oh, and z is in the upper half plane. What I'm going to tell you is that this big theta function here is going to end up basically being the key to the rest of our argument in the congruent number problem. We won't see this for some time, just because we're going to have to slowly unveil some terminology, some properties, and some facts about this function and others. But keep this guy in mind. This is going to be the key function moving forward. And from the functional equation of little theta, as an exercise, I'll give you that big theta, of course, then has a functional equation. Big theta of z is 2z over I to the negative 1/2 power times big theta of negative 1 over 4z. You can just get that directly from the functional equation of little theta and the definition of big theta. Okay, so you may ask, well, why are you bringing big theta up now if we're going to have to do a whole bunch of stuff before we even get to see why it's an important function? Why didn't you just wait to bring it up? Well, first of all, I want to be a tease a little bit, but that's not really it. The big reason is, if you rewrite the functional equation, and I'll leave this as an exercise, if you rewrite this functional equation for big theta, it can actually be rewritten like this if you square both sides. Big theta squared bracket gamma sub 1 is actually equal to negative I big theta squared, where gamma is the matrix 0, negative 1, 4, 0. Now, negative 0, negative 1, 4, 0 doesn't live in SL2Z, right? It doesn't have determinant 1, but it does live in GL2 plus. And so big theta gives us our first example of a function that's invariant under bracket gamma for some gamma outside of SL2Z. So that's really why I introduced it now. It wasn't just to be titillating or anything like that. And so now we're in a position to define modular forms for smaller subgroups of gamma. Now, we're not particularly interested in every single subgroup of gamma under the sun. We're interested in the so-called congruent subgroups of level n. So a congruent subgroup will be any subgroup of SL2Z, gamma prime, let's call it, that contains gamma of n, the subgroup of matrices that are in SL2Z and also equal to the identity matrix when you reduce their entries mod capital N. So we brought up this, we've seen this subgroup before. We're just going to say that a subgroup is congruent of level n if it contains gamma of n. All right. And what we're also going to do is sort of like how up here, when we were talking about modular forms for all of SL2Z, we defined this variable q to be e to the 2 pi iz. When we're talking about modular forms for level n congruent subgroups, we're going to need a new variable that's similar to that. It's going to be called q sub n, q sub capital N, And it won't be e to the 2 pi I z, it'll be e to the 2 pi I z divided by n. Okay. And so what's a modular function of weight k for a congruent subgroup of level n? Well, the first condition is pretty obvious. You want f bracket gamma sub k to be equal to f. Automorphy condition on modular forms that we had when we talked about modular forms for the big group SL2Z. So this is kind of expected. Okay, what's not expected necessarily is this second condition. You also want that for all gamma not in SL2Z, not in your subgroup, but actually in the full group SL2Z, f bracket gamma naught sub k needs to have this power series representation, this time not in terms of q, but in terms of q sub n. And a sub n, like before, has to be, there can only be finitely many negative index terms. And you look at this and it's not exactly what you would have expected to happen necessarily. This doesn't perfectly mirror the power series requirement we had from all the way up here when we were talking about modular forms for SL2Z. Let me bring that back up for you. Here was the condition we had. We had that this series had to only have at most finitely negative index terms. There was no bracket gamma here. There was no CZ plus D to the K or CZ plus D to the negative K. Q moving to QN is really the only difference that happens on the right-hand side. But what's the deal with the brackets in this new expression that we came up with? Well, the details are not going to be important to us, but I don't want to leave you with nothing. So I'll tell you two things. First of all, this condition is essentially checking that f is meromorphic at the cusps of gamma prime. That takes some work to see, but that's what it's checking. And that's exactly what the power series condition was checking for the full group as well. But secondly, if gamma prime happens to be all of gamma, what happens here? Well, I told you before that gamma of 1 is just gamma. In particular, n would be capital N would be 1, which means q sub n would be q, because this n would be 1 here. So this side would become the right-hand side from the original power series condition on modular forms. And what would this side turn into? Well, it would turn into f bracket gamma. It would stay the same. It would be f bracket gamma, but for all gamma in SL2Z. Okay, but if f is a modular form for SL2Z, this expression just equals f. And so we would recover the old power series condition on modular forms for the full group. Okay, so basically what I'm saying is don't worry about it. It's a meromorphicity at the cusps type condition, but also you recover the old definition of modular forms for SL2Z in the event that you actually set gamma prime equal to gamma. So it is kind of a generalization. Okay, and then, so this is the definition of a modular function for a congruent subgroup. What about modular forms and cusp forms? Well, those are just exactly what you expect them to be. A modular form of weight k will be a modular function if it's, or I'm sorry, a modular function of weight k will be a modular form if it's holomorphic on the upper half plane and there are no negative index terms in the power series, just like for the full group. And it will be a cusp form if the 0 index term vanishes, in addition to being a modular form, exactly like it was for SL2Z. And the notation for these spaces is also exactly what you would expect. So if I want to talk about the space of weight k modular forms for gamma prime, I would just write m sub k of gamma prime. Just like we had, just like we wrote m sub k of gamma when we were talking about modular forms for SL2Z. And the cusp forms are still, you know, s sub k of gamma prime. And we're not particularly concerned with modular functions. We care mostly about modular forms and cusp forms, but the notation is the same. So the only real weird unexpected thing is kind of the second condition here, but we're not going to really like be relying on that in discussion so heavily. So again, I just wouldn't, maybe think about it if you want, but I wouldn't actually worry about it. And just like with, modular forms for all of SL2Z, these are C vector spaces, they're complex vector spaces. And just like before, if F has weight K1 and G has weight K2, then FG has weight K1 plus K2. So we get the same kind of properties as we had for modular forms for the full group. One slight difference, though, is you remember there were no non-zero modular forms of odd weight for the full group. That fact is slightly tweaked when you move to subgroups. If negative the identity matrix is in your subgroup, then there are no non-zero modular functions of odd weight for that subgroup. Okay, so I mean, this happens a lot of the time, so there's not much to say there. That's a very small difference, but it's worth noting. And so we have a notion now of modular forms for actually subgroups of SL2Z, specifically congruent subgroups of level n. The next thing you want to be able to do is you want to be able to define modular forms with respect to special characters. And why is this? I initially had sort of a hard time understanding this until I saw the big picture. The real main thing is this. Remember when we defined the L function of the nth congruent number elliptic curve? It kind of looked like, well, when we defined the L function of E1, we wrote it as like the sum from 1 to infinity of b sub m to the negative s. And then there was a theorem that said, if you wanted to define the L function of E sub n for any n, all you had to do was twist these coefficients b sub m by this character chi sub n of m, which was just a Legendre symbol, basically. This right here is like the motivating reason for what I'm about to describe to you, which is modular forms that are defined sort of with respect to certain characters. It's because we're going to be doing a lot of twisting of coefficients by characters in the future. Okay. So first of all, what kind of characters am I talking about? I'm talking about Dirichlet characters mod n. We'll usually denote those by chi. And what they are is they're special types of functions from Z to the complex numbers that satisfy 3 properties. First, they have to have period n, not necessarily exact period n, but period n. So chi of a plus capital N has to be chi of a for all a. You're also not particularly interested in function values on integers that are not co-prime to capital N. So if n is not co-prime to capital N, we're going to set chi sub n to be 0. And we're also going to make sure that chi is non-zero if n and capital N are co-prime. Okay, we don't want to get trivial results for those numbers. And then finally, we want chi to be multiplicative. So we want like chi of nm to be chi n, chi m. So we want a multiplicative homomorphism. And if you want a quick exercise, you can show that for any Dirichlet character mod n, chi of 1 has to be 1. That's used so much that you almost want to add it to this list of properties here. But since you can derive it from the other ones, that's not the proper thing to do, of course. And so these are the characters we're going to be focusing on, these Dirichlet characters mod n for some n. And given one of those characters, I can define a space of modular forms kind of with respect to that n and that specific character, and it's denoted m sub k of n chi. And what it is it's a subspace of modular forms for gamma 1 of capital N. Remember, what was gamma 1 of capital N? It was all the matrices that were it was all the matrices in SL2Z that looked like 1, 1, star, 0 mod capital N. So when you reduce their entries mod capital N, you get this. So you're looking at a subgroup of that consisting of functions such that when you do f bracket gamma, you don't necessarily get f back, but you get chi evaluated at d times f. And what is this d? D is the lower right entry of gamma. Okay, and then for which gamma do we want this to be true? you actually want it to be true for everything in gamma not of n, which you have to remember what that is too. So there's a lot of definitions and things to remember here, but gamma naught was the matrices star, star, 0, star, mod n. Okay, so I know this definition in particular is a little bit to take in because you got gamma 1 flying around, gamma naught, you've got a character flying around, but you know, you use this thing enough, you just remember this. Okay, so you're a subspace of gamma 1, you've got like an automorphy condition on gamma naught, which is a bigger group than gamma 1, but the automorphy condition is loosened a little bit. You don't need to be in bracket, F doesn't need to be invariant under bracket. It needs to be kind of almost invariant under the bracket. You're allowed to twist F by this chi of D. Okay. And okay, so who cares? I mean, what's special about these spaces? A key proposition would be, well, one of many key propositions would be the following. Let's say I take a modular form for the full SL2Z of weight K, and I look at its Q expansion. So a sub n q to the n, sum over that. Then it turns out if I scale Z by capital N, then I end up with a modular form that's still of weight K, but for the subgroup gamma naught of n. So you're allowed to scale the input variable Z by some capital N, and you're actually still a modular form, just not for the full group, for a subgroup. Okay. And the second thing, and maybe more importantly, is this. You can define a new function called f sub chi, where chi is some Dirichlet character mod n. And what that is take the coefficients of f and twist them by chi of n. That turns out to also be a modular form. And as a matter of fact, it's a modular form, still of weight K, for one of these subspaces that we just defined, specifically m sub k of n cubed chi cubed. And if f happened to be a cusp form initially, so it was an sk of gamma, then f sub chi is also a cusp form. And as I recall, this is not so easy to show, but it is a fact that we will need later. So you can you can do two things. You got a modular form for the full SL2Z. You can either scale Z and get another modular form for a subgroup, or you can twist the coefficients by a Dirichlet character and produce one of these new modular forms that we just talked about up here. Okay. And this construction behaves well with respect to cusp forms. It preserves cusp forms. Here's an exercise for you. Define the trivial character to be the character sending everything to 1. Okay, that's certainly a Dirichlet character, mod whatever n you want. Show that m sub k of n with respect to the trivial character is just m sub k of gamma naught of n. That's pretty easy to show. But it's important. And we'll see why, actually, probably by the end of this page. Yeah, by the end of this page, we'll even see why that's important. Okay. So what about the structure of some of these spaces for subgroups? What do they look like? It turns out, kind of like how weight 0 modular forms for SL2Z weren't very interesting. Weight 0 modular forms for congruent subgroups are also not very interesting. Weight 0 modular forms for any congruent subgroup are just the complex constants, see? And this again kind of gives us hope that we're defining things correctly because our properties seem to be mirroring the full group case pretty well. Remember this function that I brought up last time? I probably should have waited to just bring it up until now, but there's this Dedekind eta function on the upper half plane. And it's given by eta of z is this e to the 2 pi iz, which is like q over 24. So it's like q to the 1/24th. And then it's this product, this infinite product, 1 minus e to the 2 pi nz. I showed you last time, or I told you last time, this also has a functional equation, much like the theta function. And here it is. So eta of negative 1 over z is radical z over I times eta of z. You can check that if you want. This function also, like the theta function and like big theta, will have a role to play. And here's the role right now. Suppose you have a cusp form of weight k, a non-zero weight k cusp form for gamma naught of n. And let's say n is 2, 3, 5, or 11. and then respectively, K is 8, 6, 4, 2. Okay. Then it turns out F must be a constant multiple of eta of Z times eta of NZ all to the K. And so for these same N and K values, that would tell us the dimension of the weight K cusp forms of gamma sub 0 of N is just 1. And so this eta function is allowing us to sort of understand the cusp forms more or less completely for the congruent subgroup gamma naught of N, which will again be something that will be important later. And as an exercise, in the proof of this proposition, at some point to really be complete, at some point you have to show that eta of Z, eta of 2Z all to the 8th is a weight 8 cusp form for gamma sub 0 of 2. And so you can show that. So you can try to show that if you want. Okay, you might be starting to come around to what I'm saying about modular forms for congruent subgroups. Maybe you don't quite buy into my my definition of modular forms with respect to Dirichlet characters, though. I gave you some vague reason that it has to do with twisting coefficients, and maybe you're not convinced by that. But if you're familiar with representation theory, you can actually prove the following, and this should kind of convince you that these spaces of modular forms with respect to characters are special. If you take the weight K modular forms for gamma 1 of N, then it turns out you can decompose that space into the direct sum of the weight K modular forms with respect to chi, where the sum is over all Dirichlet characters mod N. And so what these new spaces of modular forms with respect to characters allow us to do is like zoom in on this big space of weight K modular forms for gamma 1 of N and focus on it piece by piece, looking at it character by character. And as a consequence, you get something really nice out of this, which will be great for us. If you choose capital N to be 4, what happens? Well, the first thing you have to realize is, and I'll leave it as an exercise, is there's only one non-trivial Dirichlet character mod 4. So this direct sum is only going to be over one guy. And that leads you to the following proposition. The weight K modular forms for gamma 1 at level 4 are actually just the weight K modular forms with respect to the trivial character at N equals 4, if K is even. Okay, if K is odd, then the weight K modular forms for gamma 1 of 4 will just be the weight K modular forms at 4 for this non-trivial character chi. And so I guess what I'm trying to get across here is when capital N equals 4, you kind of lose the direct sum. And there's only one actual component to look at. And this, again, this is going to be great for us when we actually start talking about half integer weight modular forms. This simplicity in the capital N equals 4 case is going to be great. Now that I've gotten this out of the way, the simplicity in the capital N equals 4 case, I can bring up big theta again, and I can tease you a little bit more with it. So, well, okay, so if big theta is so important, we might ask ourselves where it lives. Does it live anywhere? Well, that's not actually the natural first question you want to ask. The first thing you want to ask is, if I square big theta, where does it live? And let me give you some motivation for why squaring it would be a natural thing to do. Go back up here. The functional equation that we have for big theta is most succinctly and nicely represented in the language of modular forms using the square of big theta right here. So that's why it's natural to square big theta first and ask where that lives, because it's got this nice automorphy condition for this matrix here when you square it. So where does big theta squared live? Well, it actually lives here. So proposition 22, big theta squared is a weight 1 modular form of gamma sub 1 of 4, which by the proposition above we know is just a weight 1 modular form at level 4 with respect to the non-trivial character mod 4. Okay. And I'm going to stop teasing the function now, but I'm just going to try to bring up properties of this function kind of piece by piece as they become relevant once we define things that make it relevant. So more on big theta later. I'll keep teasing it for now. And now that we've got a bunch of definitions out of the way, so modular forms for the full SL2Z, modular forms for level n congruent subgroups, and modular forms for with respect to Dirichlet characters mod n at level n. Now that we got all those definitions and constructions out of the way, we can actually start to do some serious damage on the congruent number problem. So here's the setup. The setup is this. If I have a modular form, I have weight k for the congruent subgroup gamma 1 of n, and I write its Q expansion out. And I impose the extra restriction on this Q expansion that the coefficients and absolute value are like big O of n to the c for some real number c. That allows me to define the following object, L sub f of s, which I want you to think about as the L function of the modular form. And what it is you make an infinite sum with the same coefficients that your modular form had, the a sub n, but you want to turn it into an actual L function looking thing. So you replace the q to the n by the n to the negative s. Okay. And if you remember, what do our L functions for our congruent number elliptic curve look like? They look very similar, right? They look like this. They've got coefficients times integers to the negative s power, and the sum is over, as many indices as there are non-zero coefficients here. So we've got a striking similarity between this so-called L function of a modular form for the subgroup and the L function of an elliptic curve, basically. And as a matter of fact, because of this big O condition, you can show this guy converges for a real part of S bigger than c plus 1, which is great. We don't want to just define an infinite series and then it doesn't converge anywhere. So this expression should be familiar to you. In fact, I told you when we were studying L functions that we would see series like this again. And here we are, seeing them again. And they have a name, series that look like this in general. So these L functions of modular forms and these L functions of elliptic curves, they kind of have the same form, and they're called Dirichlet series. And a kind of disturbing or surprising thing that you end up with is the following. If you use Mellin transforms in their inverses, you can show this theorem. So let F be as above. Let it be one of these modular forms. Okay. Satisfying this condition, this big O condition on the coefficients. And then you're going to let capital lambda of S be radical n over 2 pi all of the S times the gamma function evaluated at S times the L function of F evaluated at S. Look familiar, anybody? This was the exact same capital lambda, more or less, that we defined when we looked at the functional equation and the analytic continuation of the L function of an elliptic curve. More on that in a second. Then this guy extends to an entire function. And the L function of F has a functional equation. And it looks strangely similar, familiar to us. Lambda of S is C times lambda of K minus S for some constant C. If you go back through the notes, though, and you look at everything I said about L functions of elliptic curves, you discover the following. This is the exact same functional equation satisfied by the L functions of my congruent number elliptic curves, with K equal to 2, capital N here equal to 32 little n squared if little n is odd, and 16 little n squared if little n is even. And then C was either 1 or negative 1, depending on whether or not n was 1, 2, 3, or 5, 6, 7 mod 8. In terms of Legendre symbols, C was negative 2 over n if n was odd, and C would be negative 2 over n over 2 if n is even. Check this. Check this is equivalent to the original definition I gave you back when we talked about L functions of elliptic curves before. And it's also an easy check that the L function of any congruent number elliptic curve satisfies this big O condition, right, where did I put it? Right here, for C equals 1/2. And so it's like this very natural L function we defined for a modular form. It seems to be matching up exactly with what we were doing in the elliptic curve case, like perfectly. We have like all of these conditions, or we have this condition satisfied. We have the same looking series. We have the same functional equation. We have the same capital lambda, more or less. I mean, everything's falling into place. And so this immediately begs the following important question. If I start with any Dirichlet series, so any series of this form, forget not even an L function, just any series that looks like this, okay? And I happen to know that it has some nice functional equation in this sense, something more or less that looks like this, okay? Do the coefficients of that modular form of that Dirichlet series come from the coefficients of a modular form? In other words, is this Dirichlet series actually of the form L sub f of s for some modular form f? Do the coefficients match some coefficients in some Q expansion for a modular form? And well, an elliptic curve whose L function, for example, has coefficients coming from the L function of some modular form under the setup we just described is called a modular elliptic curve. And now we can actually finally understand one avatar of the famous modularity theorem for elliptic curves that I've been teasing for several weeks now. The theorem that says every elliptic curve over Q is modular. In other words, every elliptic curve over Q has an L function whose coefficients come from the L function of some modular form. And if you take that theorem, the modularity theorem, and you combine it with this Ribot's level lowering theorem, you get Vermont's last theorem. So obviously I'm not talking about Vermont's last theorem so much in this talk, but it's still, I have to mention this here. This is crucial. And so if I go back to the question I asked here, if I start with a Dirichlet series with a nice functional equation, is it the L function of some modular form? If the answer to that question is yes, then what does that imply? That implies that the L function of my congruent number elliptic curves, which is itself a Dirichlet series with a nice functional equation with k equal 2, its coefficients must be the coefficients of the Q expansion of some weight 2 modular form, if the answer to this is yes. And so what that means is the second I get an affirmative answer to this question, I can move all of my analysis about the congruent number problem from elliptic curve land to modular form land. And I get all of the tools of modular forms at my disposal. And so the first thing to note would be that the modularity theorem, of course, tells you that the answer to this is yes, because your congruent number elliptic curves are over Q. But there's two problems. Well, there's three problems with that solution. The first one is we don't want to kill a fly with a nuke. Okay, we don't want to invoke the modularity theorem to prove a much easier theorem if we don't have to. Second of all, the modularity theorem, as I presented it, does not give you that the actual modular form is weight 2. It just gives you that the coefficients come from some modular form. Okay. Now, it turns out the modularity theorem does have something to say about the weight of the modular form. But the third problem with this is the modularity theorem wasn't known at the time all this was shown and written up. So we're not going to invoke that. We don't need that much power to continue. However, to give you the theorem that you are going to need to continue, we're going to need some more definitions. Definitions. That's the name of the game in modular forms. So if I write chi sub 0 from now on, that's going to be a fixed Dirichlet character mod capital N. If I write chi from now on, I'm thinking of that as like a variable Dirichlet character with conductor lowercase m. And what is the conductor of a character? It's the smallest natural number dividing this capital N. So we'll call that number k. such that there is an actual Dirichlet character, say chi prime, mod that number k, mod the conductor. I probably should have just called this m, right? Like, what am I doing? It's called m right here. Then I changed it to k for some reason. For which the values of chi prime at a equal the values of chi at a, as long as a and n are coprime, a and capital N are coprime. If you don't, there's a nicer, more elegant way of saying this in the literature. It's the conductor is the smallest natural number m, such that chi is induced by a primitive character mod m. Okay. Now, that's nice, fancy, elegant language, but you need to know what all that means. So this first description is what that actually means. Okay. So it's like it comes from a character that's a Dirichlet character mod this smaller number that divides capital N, and there is no smaller number. Okay, that's what the conductor of a character is. Okay, this is just a technical condition you don't really need to worry about, but I guess it's something that you want to be aware of. In our specific setup, we want to make sure that our conductor is either an odd prime, or if capital N is odd itself, we do allow the conductor to be 4. You're never going to see that again, but I just wanted to mention that. I'm going to define a large set of values of M to be a set containing at least one M in every arithmetic progression, U plus JV, where U and J are integers. This should say U and J are integers that are any, oh, I'm sorry, no. With J an integer, that's right. And then U and V integers that are coprime. Okay. So I want a large set of values of M means take at least one from every single one of these progressions. And by Dirichlet's theorem on primes in arithmetic progression, every single one of these progressions has to contain a prime. And so that leads us to the definition of a large set of primes. A large set of primes will be a set of primes which contains at least one prime for every single one of these progressions. Okay. And if you put all of that together, you end up with the definition of a large set of Dirichlet characters. What is a large set of Dirichlet characters? It's a set of all non-trivial Dirichlet characters mod M. So all non-trivial Dirichlet characters mod M, for which M, a large set of values of M. And we've already defined a large set of values of M up here. Okay. And we got to keep going here. There's, to give you this, the theorem's coming up right here. Okay, so I have to give you more or else you're just not going to understand the statement. We're going to let C be plus or minus 1. We're going to let chi be a variable, Dirichlet character of conductor M, just like it was up here when I initially defined it. Okay. And we're going to define C sub chi to be C itself times chi naught evaluated at M. Remember, what's chi naught? Chi naught is a fixed Dirichlet character mod capital M. Okay. So chi naught of M times chi, the character I have here, evaluated at negative N. Okay. Times this G of chi over G of chi bar. What is this G of chi? It's the Gaussian sum of the character chi, which if you really want to know, here's the expression. You add up all the values of chi of j, starting at j equals 1, and you multiply by this e to the 2 pi ij over n. Okay. And then chi bar just refers to the complex conjugate of the character chi. So lots, I apologize severely for all the terminology and definitions, but you really do need it. And so we've got that out of the way. So now I'm going to take f. I'm going to take some function f that has a Q expansion. I'm not necessarily going to require that it's a modular form, but I am going to require that it satisfies the big O condition on the coefficients that I had from above. And I'm going to define L sub f to be and lambda of s to be exactly how I define them up here. L sub f will be the Dirichlet series made out of these coefficients, just like it was when f was actually a modular form. And capital lambda will be this exact expression right here. Okay. Okay, so those definitions are not changing, but I'm going to introduce two final definitions. I'm going to introduce the notion of the L function of f twisted by the character chi and it's not hard. I just take the L function of f and I twist all the coefficients by chi, evaluated in n. Okay, and n is my summation index. And then I'm going to define capital lambda twisted by chi in a similar way. It's going to be almost the exact same thing as capital lambda was up here. Two differences though. L sub f will be replaced by L sub f twisted by chi. And then you're also going to end up here with the conductor multiplied by radical n. So those are the only two differences. You can see those reflected here. Here's the m and here's the twisted L sub f. So in other words, twist lambda and L sub f by chi. That's really what you're doing to produce these two new objects. Okay, so the theorem we need to answer our question from earlier about whether or not Dirichlet series come from modular forms is the following very hard theorem of Weil. I went through the proof of this and it was like a nightmare. This is not in Koblitz. If you would like a source for this, you need to read Ogg's 1969 lecture notes. And really, once you read Koblitz, you only need to read sections 1 and 5, but still, it's a lot. So let me write that. And here's what the theorem says. Okay, so let's say I have f with a q expansion starting at 0. Okay, it's not necessarily a modular form. It's just some function with a q expansion. But I know it satisfies the functional equation from proposition 23 for some n and k and for c equals plus or minus 1. So this functional equation right here for some capital N, for some k, but we're going to require c is plus or minus 1, which, by the way, notice that the L function of our elliptic curves, c was plus or minus 1. Okay, so that's good. And we're also going to require that these coefficients satisfy our big O condition, which is something we've been requiring for the last 15 minutes. Okay. We're also going to suppose that when you take lambda of s, this guy from up here, okay, you take lambda of s and you add a naught times this weird expression 1 over s plus c over k minus s. That's a technical thing that has to show up in the proof of this theorem. We're going to require that that extends analytically to an entire function. And not only is it entire, but it's bounded on every vertical strip in C. A function that satisfies this property is called an EBV function, by the way. So from now on, because I'm going to refer to it one more time, I will call that an EB. It stands for entire and bounded. Okay, on entire and bounded on vertical strips. That's what EBV means. We're also going to suppose further that for a large set of chi, which we've defined precisely up here, okay, that the twisted version of lambda without this extra garbage extends to an EBV function satisfying a very similar functional equation. This functional equation looks a lot like the one we had above, which was just lambda of s equals c lambda of k minus s, right? But we're replacing lambda on both sides by the twisted version of lambda, on the left-hand side by chi, on the right-hand side by the complex conjugate. And we're replacing c by the c sub chi that I defined up here. Okay. So basically, f has a nice functional equation and extends analytically, and so does its twisted version. Really, if you boil it all down, you can kind of just say it like that. Then f is a modular form of weight k at level n with respect to the fixed Dirichlet character mod capital N from earlier, chi naught. In other words, yes, these coefficients do come from a modular form if all these huge assumptions are satisfied. And furthermore, if L sub f, the so-called L function of this f, converges absolutely for a real part of s on some right half plane, real s bigger than k minus epsilon for some epsilon positive, then not only is f a modular form, it's actually a cusp form. Okay. And I'm going to end today with the following theorem. Theorem the L functions of our congruent number elliptic curve satisfy every single one of these conditions. Furthermore, we've already seen that most of them are satisfied. And here are the specifics. It satisfies all, they satisfy all of the above conditions if you let chi naught be the trivial character, k equal 2, little c equal 1/2 in the big O condition. A naught is actually 0, so you lose this completely. Capital C is plus or minus 1. We already knew that. Capital N is, what was it? Is 16 little n squared if n was odd, 32 little n squared if n was even. I might have said that backwards. 16 n squared if n is even. I said that backwards. 32 n squared if n is odd. Okay. And what is F? F is the following. Remember, the L function of E sub 1 was given by this expression here starting at 1, B sub m to the negative s. So it's a Dirichlet series in particular. But then we had a theorem that says the L function of E sub n was the twisting of that by this Dirichlet character chi sub n evaluated at m. And so F will be the modular form whose coefficients are these coefficients here. Okay. So the Q expansion will have these coefficients. And as I remarked here, the L function, we've already seen that these L functions satisfy all these conditions. The only things that we have not shown are this second functional equation and this second analytic continuation. We haven't shown either of these. But as it turns out, you can go through the proof that the first analytic extension happens and that the first functional equation is satisfied. And you can make very small modifications to those proofs, and you will get the second functional equation and the second analytic extension for free. And so exercise, go back through all the notes from all the lectures and convince yourself that all the rest of this has been shown. As a matter of fact, we've also shown this absolute convergence condition for epsilon equals 1/2. And so what is this theorem telling us as a conclusion? It tells us the following. The L function of our congruent number elliptic curves, which is given by the sum from 1 to infinity, m equals 1 to infinity, chi sub n of m, where chi sub n is a Dirichlet character of conductor m, and it is the Legendre symbol character, if you go back and look. B sub m to the negative s, where B sub m are the coefficients of the L function of E1. These coefficients they arise from a cusp form of weight 2 for gamma naught of n, where n is 32 little n squared if n is odd, and 16 little n squared if n is even. Chi sub n, remember, is the Legendre symbol. It sends m to n over m if m is odd, and it's not defined if m is not odd, so we would set it to 0. And so there you go. Our L functions are not just any old L functions anymore. Their coefficients come from a weight 2 cusp form for this level capital N congruent subgroup gamma naught. Why gamma naught, by the way? You might say that's not what the theorem says. The theorem says it should be an S sub k n with respect to this character chi naught. But what I'm telling you here is chi naught is the trivial character, right? And by this exercise up here, I wrote it somewhere. Where is it? It's like right around here somewhere. Oh, by this exercise right here, m sub k at level n of the trivial character is just the full set of all modular forms of weight k for gamma naught of n. So that's why we get this, okay? Because our character incidentally happens to be trivial in Bayes' converse theorem applied to our situation. So our L function has coefficients that come from a weight 2 cusp form for a level capital N congruent subgroup. That's what we've learned. And so there's our bridge. So starting next time, we're going to be able to take all of our analysis about the congruent number problem and move it from the study of elliptic curves, completely port it over to the study of modular forms. And I think that's a great, perfect place to stop today. So I'm going to stop recording. If you have any questions, type them out or unmute yourself, and I'll do my very best to answer them. And thank you again.